try to understand clearly. I think while I'm teaching, I think there is no, you may not get any doubts. I think I sure I can say that. See here, this is I can say this is very important designing method for you in all domains. While you are working in any domain, you are going to work on this dynamic programming algorithms. Actually, what exactly this concept? Now I'll explain with small examples and try to understand clearly what is exactly the dynamic programming. Then we'll go to the theory. I'll tell you here. For example, let us take in divide and conquer. Let us take in divide and conquer. In divide and conquer, what we have here, just we have only that first divide, then second and solve the solutions, sub problems. Third, combine. Only these three steps are there in divide and conquer. Is it? But in case of greedy method, what we have here, we are going to select one solution and we are going to check feasible solution or not. And we are going to add, if it is feasible, we are going to add into your solution vector. These are the three steps. But here what happens, and here what happens, I'll tell you. For example, if I'm going to apply one in divide and conquer for one problem, let us take this is my array. Let us take. I want to calculate. I want to sort this array. What I'm going to do here, I'm going to divide this array into parts, subproblems. This is one subproblem, and this is one subproblem, and this is one subproblem. Like that, we are going to divide problem into subproblems, problem into subproblems. Okay. Now you are going to solve this subproblem, and you are going to solve this subproblem, combine it. Then you may get the final solution. Okay. Are you clear? That is in divide and conquer. But in case of greedy method, you know well, it is not related to that. This is the primary condition for divide and conquer is the nature of the problem should be divisible problem. Okay. But if it is not divisible, what we have to do? We go for the greedy method, you know well. Okay. We have to go for greedy method. Now, in dynamic programming, what we are going to do here? In dynamic programming, what problem also is there? Okay. Now I'll tell you one example, small example. Let us take this is my my graph. Let us take this is yes, and this is some graph. Let us take this is this, and this is this. Okay. This is one graph. Let us take. Now I want to calculate. These are the directed graph, and weighted graph. Each edge that we have a weight. Let us take this is 10, this is 12, and this is 5, and this is 6, 2, 10. Let us take each weight, each edge that we have a weight. I want to calculate the distance between shortest distance from S to some this terminal. Okay, sync. Okay. Now, in case of it is also we can divide, but by division we can't each take. For example, here what we have here. Let us take a divide and conquer. The problem we are going to divide into subproblems and solve this subproblem, and these solutions we are going to add, and you may get the answer. But here subproblems are, this is very important point you please. These subproblems are independent subproblems. Independent subproblem. For example, this is not depends on this. This is not depends on this. This subproblem is not depends on this. This subproblem is not depends on this. These subproblems are independent. But here, if I want to divide this problem into subproblems, let us take. If I want to divide this problem into subproblem, this is one subproblem from yes to this one to from here to here. This is one subproblem. This from here to here is subproblem. If I solve only these subproblems are not independent. These subproblems are not independent. These subproblems are dependent subproblems. Why? Because if I want to calculate the solution for this subproblem, I require this. Why? Because I'm starting from here. I'm starting from here. Yes. Okay. I require this. What is subproblem solution? And you have to add to here. Then you may get the shortest distance from S to here. Okay. For example, if I want to calculate the distance of T, let us say from S to T, you require this one and this one. That means what here, what you have find here, subproblems, you can divide the problem into subproblems, but subproblems not independent. This point you please remember. Are you clear? What you have find this divide and conquer and dynamic programming? Be clear. In divide and conquer, we are going to divide the problem into subproblems. This is one subproblem, this is one subproblems. But this subproblem is independent with this subproblem. And you can solve this subproblem separately, and this solve the subproblem separately. You can combine it. Okay, are you clear this point? But here we can divide this problem into subproblems. Up to here, this is one subproblem. Up to here, one subproblem. From here to here, one subproblem. But if I want to calculate the solution of this subproblem, you require from this solution also. If I want to calculate the solution of this, you require this solution also. If I want to require all these, that means each subproblem is not independent here. Are you clear? What is the difference of divide and conquer and this? Now what happens? Okay, this subproblems are not independent. That's why I'm going to use one separate technique, dynamic programming, dynamic programming. But okay, you can ask one more question, sir. What is the need of applying this divide and conquer for this problem? There is a greedy method, no? You can use greedy method. You can use greedy method, right? That is also correct. We can use greedy method. If I use this greedy method, what happens? I'll tell you. Now, for example, if I'm using greedy method for this. I'm using greedy method for this. What happens? I have to select a solution. I have to select a solution where I'm staying at this place. I'm at S now. I will select a solution of this S to this stage. Let us take. Among these three, this 5 is less. I'll move to here. Then from here, if there is two stages are there, let us take this 10, this is 11. 10, 11, this is less. That's why I'll move to here. And from this, it is away. That means what? By using greedy method, what happens? You are at one place. You are not moving according to stages. You are at starting place, and you are deciding that from this stage to this stage, what you are to, where you are to, which way you have to go. From this stage to this stage, which way you have to go. That you are going to decide at this place only, and you are going to decide at this also. Finally, you may get a conclusion, sir. 5 plus 10 plus some 2, let us take 2, it is equal. 5 plus 10 is 15, 15 plus 2 is 17. 17 is a minimum shortest distance, minimum distance from S to T. That is the greedy method. Greedy method is nothing but I'm not going inside of that each and every stage. I'm at top end, this end. I'm calculating what is less, what is less, what is less. That's all. That is nothing but that's why this we call as static method. This we call as static method. Statically, I'm not moving according to the stages. I'm not taking decisions according to the stages. I'll take an decision at starting point by seeing the lengths. That's all. Okay, are you clear? This we call as static method. Now, I'll tell you two, three examples on this also. You don't worry. But here, this 17 is wrong. This will not give always optimal solution or minimum distance. there may be a minimum distance like 10 also may be there. In that case, how you make it this 10? How you make it this 10? For that, we are going to apply one dynamic approach. One dynamic approach. That approach we call as DP, dynamic programming. What dynamic approach will do here? What dynamic approach will do here? Just from at 5, at yes, it is going to take a decision on this stage only. Whether we have to go this or this or this or like that. Then after that, it moves to here. It takes the previous solution as storage. Previous solution already is there with this. Then again, it may take addition on this next stage, and it adds adding with this previous solution also. And again, it moves to here. It have the previous solution of this distance and take addition on this. That means dynamically in each stage, at each stage, it is going to take addition. That's why this we call as sequence of decisions. Sequence of decisions. The optimal solution is nothing but in dynamic programming, it is equal the sequence of sum of the sequence of optimal solutions. Are you clear my point? In static, you are not doing like that. You are not doing like that. You are not keeping even previous value also. But in case of dynamic, you are keeping the previous what you have calculated and you are taking this as a consideration and you are taking a decision on this. Very clear. That is dynamic. That's why in dynamic, what do you require here? What do you require here in dynamic? You please see here. Whatever solution you have, that you have to store and reuse. Store and reuse. You have to store this solution and you have to use for the next one. That means whatever solution you got in this stage, you store this solution, you have to use for this. Okay, you have to store this solution, you have to use for this. That's why store reuse method also we may use in dynamic programming. Very clear what exactly the difference in divide and conquer and dynamic programming and greedy method. How you are going to sell it. But I'll tell you here, the dynamic programming will give you a best result comparatively greedy method. I'll tell you how it is. I'll tell you with one example. Very clear this point? Very clear? Now, finally, we can conclude this. This even in dynamic programming, we can divide the problem, first one, and second one, we can solve this particular solution, but that means from this stage to this stage, and you have to store it, and third one, reuse it. That means here also in divide and conquer also we are going to solve the sub problems. We are going to combine it. But here what you are going to do, you are going to solve the sub problems and you are not combining. You are reusing this. Reusing to get the next one. Get the next solution. Using this sub problem solution to next solution. But here whatever sub problem solution is there, directly independently, this plus this will is the solution for divide and conquer. But here we are not doing like that. Are you clear this point? Are you clear this point? It is you are going to get effective or efficient result or optimization problems. Okay. Now, one more point I'll tell you. Here, this method, DP, dynamic programming, we are going to use for most of the optimization problem. Optimization may be minimize or maximize. We are going to use minimization problem and optimization. For example, if I'm going to use this for 0 by 1 knapsack problem. In knapsack, what do you require? You have to optimize the problem. Let us take above problem, this problem. In this problem, what do you require? Minimum distance. That means what? You have to use this concept for minimization problems and maximization problems. Very clear this point? And one more point I want to share with you here. Divide and conquer and greedy method and DP, dynamic program. Once you see this in divide and conquer, greedy method, DP, what happens in divide and conquer? What you are doing? Total big problem. I am going to divide into parts. The solution is from you are starting from sub problem. That means you are coming from top to bottom, sorry, bottom to top. That means this we call as bottom up approach. Are you clear now? In case of DP, also what you are doing, what I told you, first divide the problem and take sub problem. The solution of the sub problem you have to use for this. That means again you are going to move from bottom to top. Move from bottom to top. Very clear. Are you clear this point? Then this we also call as bottom up approach. This we also call as bottom up approach. What do you call this greedy method? The greedy method, what I told you? I told you. What I told you? I'm not moving down. I'm taking at a statistical level. I'm going to take a decision on this. That means this is a problem. I'm taking a decision of this problem without moving down, taking solution of each one. That we call as greedy method. That we call as top down. This approach we call as top down. Divide and conquer is bottom up. Dynamic programming is bottom up. Then greedy method is top down. Are you clear what exactly this? Are you clear? Now you can go for the clear and everything theory is there that you can see one by one but slide. The concept is this one. Are you clear? Once again listen. Dynamic programming. Finally, what are the conclusions here? Dynamic programming we are going to use for a sub-problem is not independent. That's first one. Second problem is we are going to use for dynamically if I want to take a decision. That means that is sequential. The decisions are in sequence. In that case, you can use this dynamic program. And dynamic programming is top bottom up approach. Okay. Then dynamic programming is it is one more principle is that we call as principle of optimality. This I'll tell you clearly. Principle of optimality. What do you mean? I'll explain clearly what exactly. Without this principle of optimality, nothing is there here in dynamic. What do you mean that? Here, once you see this is a problem. Here, this is yes, and this is one stage, and this is second stage, one stage, and this is timeline. Now, what happens? What you are doing here? If I want to calculate this distance, this solution, you are using this one, and you are taking this as input to this, and this stage, you are taking this as input for this stage, and you are going to calculate this distance. And you are taking this solution as input for this stage, you are taking a decision on this. You are taking input as this one, you are taking this. What do you mean that? That means what? If I'm going to divide the problem into subproblems, I'm taking decision. If I want to calculate addition of one subproblem, I'm going to take addition of previous subproblem. That means what? The output of one subproblem, previous subproblem, is taken as input for the next subproblem. That means what? If I want to calculate this stage, this I'm taking as input for me. What I calculated previously, that I'm going to take it as input for me. If I want to calculate this I'm going to take it as input for me. That means what? One stage output, you are going to take it as input for second stage. You are taking output of second stage is taken as input for third stage. That we call as optimality principle. If the problem is holding this optimality principle only, you have to use the dynamic program. Without this optimality principle, if problem is not hold this optimality principle, you should not use dynamic programming. This point you please clearly mention. Are you clear? What are the points you have covered now? One is subproblems are not independent. And second is if you require sequences of solutions. And third is where the problem is holding optimality principle. Then only we are going to apply the dynamic programming. Okay. Now come to the theory part. Now also see here this dynamic programming, the term, even the name, the author is Bellman, Richard Bellman. Why? Because Bellman is scientist who developed the principle of optimality. Principle of optimality, we also call as Bellman principle of optimality. Okay, with using this principle of optimality, we are working on this one dynamic programming. That's why this we call as uh, Bellman's principle of optimality, developed by Bellman in 1955, not now. And in your examinations, we may ask you what is the control of abstraction of dynamic programming. Only that simple. Here there is no algorithm like your divide and conquer. In your divide and conquer also maybe have an algorithm, general method for divide and conquer, control of abstraction for divide and conquer. In greedy method also is there. Control of abstraction for greedy method, general method for greedy method. One point is very clear: general method, control of abstraction, both are same. Okay? But here there is no specific algorithm. Only these two. This will gives you control of abstraction. What do you mean that? It is one algorithmic design method that can be used when solution to a problem can be viewed as a result of sequence of decisions. I already told you. That means what? One stage, one result. Then after that, one more result. After that, one more result. After that, one more result. That's why this we call as sequence of decisions. Okay. That's why this we also call as dynamic programming. Okay. Now, how you may get this sequence of decisions? Sequence of decision in the sense one term is depends for term. This term is depending on this. This term is depending on this. This term is depending on this. This is nothing but what? Recurrence equations. This is nothing but recurrence equations. Are you clear? This is nothing but recurrence. That's why what you are doing here, you have to develop the dynamic programming recurrence equations to solve the problem. You have to develop dynamic programming recurrence equations to solve the problem. Okay. Now, I already told you principle of optimality. This is very very important in your examination. For 2 marks, we will give you this question. This question will give you 2 marks. What? Once again, listen. What is this principle of optimality? For example, this is stage one. Let us take. This is stage two. Let us take. This is stage three. Now, whatever input you have taken at stage one, whatever output you are going to get, this is input. Output you are going to get. This output you have to take it input for stage two. This output is taken as input for stage two. This is stage two. This is stage one. This is stage three. The output of this stage, you can take it as input for third stage. This is third stage. This process we call as principle of optimality, developed by Cada. This principle we are using in our dynamic programming. All problems, whatever we are solving in this dynamic programming, we are using this principle of optimality. I'll tell you where we are going to use. Yeah, I'll take one problem and where exactly we are using this principle of optimality in that problem. I will explain. Don't worry about that. Okay, now you clear? If principle of optimality is not hold in the problem, it is not obeying this problem, we cannot use dynamic programming. Without principle of optimality, dynamic programming we cannot use it. This point you please remember. Okay, are you clear? Then what you have to see while you are applying dynamic programming solution, the first you have to see whether the solution is going to hold the principle of optimality, and you have to see that you have to develop that dynamic programming recurrence equations. First you have to see the optimality principle. Then you have to see the dynamic programming recurrence equations. Recurrence equations can we develop or not? Want to see that. And each equation You have to develop one optimal solution. This is optimal solution. Each recurrence you have to see for optimal solution. If you are not getting this optimal solution, and go back, trace back, trace back, and construct the optimal solution only. Then it will give you optimal solution for you. Okay, are you clear at this point? What you are doing? Then where we are going to use? I already told you. We are going to use for optimal solutions. Optimal solution in the sense what? It may be maximization problems and it may be minimization problems. Maximization problems we can use, minimization problem use. I already told you maximization problem, let us take, that is the knapsack problem. In knapsack problem, what do you require? You require to maximize the profit. In case of shortest path, you have to calculate, always minimize the shortest path. This is minimization problem. This is maximization. Are you clear? All these, both the cases, we can use the dynamic programming. Then, what are the algorithm for dynamic programming? In algorithm for dynamic programming, you please remember this. You can write for abstract. Sorry, control of abstraction. These points also you can write for control of abstraction or general method. Are you clear? First, what you have to do, characterize structure of optimal solution. That means you have to develop the recurrent solution. Then recursively you have to define, while you are developing recurrence relation only, recurrence relation, that you are going to develop the recursive solution, that you know that, and compute the optimal solution on this one. Then consider the optimal solution for this side. Okay, these are the points I already explained. And what are the applications? What are the applications of this? First application is multi-stage graph, and that means we are going to discuss in our unit. In our unit, we have to discuss this multi-stage graph. Now there is second two problems. Actually, as per syllabus, we have 5 problems. I think one is multi-stage graph, and second is OBST, optimal binary search tree. Then third is matrix chain multiplication, reliability design, 0 by 1 knapsack, multiplicative optimization. These are the problems to be discussed in dynamic programming. Actually, many problems are there. According to your syllabus, you have only 6 problems. Okay, these 6 problems one by one we'll discuss. And where exactly we are going to use this dynamic programming concept in real world applications. Very, very important thing you please remember. Without knowing applications of one concept, you should not know it. There is no need to know. This point you please remember. Here, the first point is we can use this same concept, dynamic programming, in Google Maps. Google Maps in the sense whatever Ola cabs and Uber, everything, all are they are using shortest paths to your source and destination. They are calculating this. How they are calculating? Inside, they are using the DP problems, dynamic programming applications. Okay. Now, if I want to transfer the data from source to destination, how, in what way, with shortest distance, it is very within quick, we have to send the data. How it is possible? It is by using again the DP algorithms. Then all optimization problems and routing algorithm. This is very, very important. Even electrical department students also they are going to use this routing. They're using this dynamic programming for their routing of poles and document the distance measure. That means, for example, if I want to compare the two documents, whether they are matching or not. For example, revenue department is there, they're match, you will see that whether document is correct or not, whether document is correct or not. How they can check? I substituted, I given one document and they have their own document. They will compare this document with this document. How they may compare? They are not going to compare each and every element. They are not going to compare each and every this one. They may calculate the distances, distances between the terms, and the distance between the terms, and then the distances they will compare. Okay, for that purpose also they may use the DB dynamic program. These are the different applications where we are going to use this dynamic program. And the comparisons, I already explained what is the difference between the major comparison is DP and divide and conquer and greedy method. Only three methods. In divide and conquer, I already told you, you are going to divide and independent subproblems you are going to solve it and combine it. That you are going to do in the divide. But in case of DP, just subproblems you are going to solve it, but you are going to store this subproblem for future the next calculations. We are not going to combine these subproblems. We are going to store this subproblems solution, and we are using this solution for future calculations. That is DP. In your divide and conquer, you are going to calculate the solutions of each subproblem and combine it. Okay, that is the difference. And I already told you, in the divide and conquer, all are not independent. So these are in divide and conquer, all subproblems are independent. It's fine, you please remember. In case of dynamic programming, the subproblems are not independent. Not independent. In that case, we are going to use a dynamic programming. Okay. Now come to these are the differences. Okay. This you can read yourself also. We can divide the same thing. It is a top-down approach. I already told you, divide and conquer. Top-down, bottom-up approach. And this is whatever we have discussed with examples. No? These are the different solutions of that. I combined at one place what table I given to you. And in case of this is very important, I forgot it. Here, for example, there is a solution like this. This is one stage, and this is one stage, this is one stage, and this is a solution. This is one stage, let us say. But in case of greedy method, what we are going to do, you are going to stand at this place, and you will take a decision from these to this, and this to this, and this to this. Okay, this decision we call as local optimal. Local optimal. That means what? You stand at this place, but you have taken a decision on these three, and you've taken one. But you are not considering all these points. You are not considering all these points. You are not working on globally optimal. You are working on locally optimal. Be clear and combined. But in case of a divide and conquer, it's not like that. You have calculated the shortest distance from this stage, and while you are calculating this, you are going to use this distance for this second stage, and you are using this distance for third stage. That means you are working on globally optimal. Are you clear? This we call as globally optimal. Okay? This we call as locally optimal. That's a basic difference in your dynamic program. I already given to you. This is a bottom-up approach, and this is top-down approach. I already told you. Clearly, you please listen. Now try to understand what exactly I'll tell you. Still, you have a doubt. Sir, already greedy method is there. What standing at one place and taking decisions of phases, and what in dynamic programming exactly doing, and how you are going to get efficient result than greedy method. Still, you have many doubts. I'll tell you one example. I'll explain this concept with 2-3 examples so that you can understand what exactly greedy method is using and how dynamic programming is using and giving one efficient result of this. Okay? Now let us take this is one graph. It is one graph. We want to calculate the distance between V2 to V3. This is from here to here. We have different paths are there. From here to you can go from this side, this side, this side. You can go from here to here. You can go this side, this side, this side, this side. You can go. From to here, you can go like this. But in greedy method, what you may do? In greedy method, shortest path how you may calculate. I'll tell you. In greedy method, you can calculate. Once you see that this is from this to V not to V1, you can say among these three, which is a minimum. One is a minimum. You may take this one. Among these four, which is a minimum. Two is the minimum. This is you may take. From these three, which is a minimum. Four. This is 7. Okay. This is a greedy method. How we are going to solve. Okay. Each stage you are going to take a decision on that. Then you are going to add it. Okay. That is a greedy method. But in case of in that case, that is a final distance. I'm not denying that. If you take one more problem, let us take here. This is V2, V0. This is V3. I want to calculate the distance between V0 to V3. Let us take here. Now what happens? Also, let us take this is V0 is stage 0. This is stage 1. This is stage 2, and this is stage 3. That's why this we call as multi-stage graph. Many stages are there in this graph. That's why multi-stage. Stage 0, stage 1, stage 2, stage 3. Okay. Now I want to calculate stage 0 to stage 3. Okay. The distance between minimum distance. Not distance in the sense anything you can calculate, but minimum distance between V0 to V3 I have to calculate. Okay. In this case, what happened? I'm applying the greedy method here. I'm applying greedy method here. Now what happens? Now here in greedy method also see V0 among this one which is the V1 V0 2. I'll go among V157. One is minimum. That's why it is a pass. One I take it. 1 plus. Next from V1 to 2, only 2 pass are there. This is 5 and this is 16. That's why 5 I think this is 5 or 16. 9 I think. This is 9. This is 16. Okay. 9 I take it. V0 to V. This is 1. V21 to 1. Where is this 9? This is 1. 21 to V3 at move. V21 to V3 is only one way 13. Now what you make it? 1 plus 9 is 10. 10 plus 13 is 23. By using your greedy method, you may get 123 as your path. Okay. Are you clear this point? Are you clear? Now, but actually the optimal solution is what? Actually, optimal solution is what is optimal solution for this? Once you see that, actually, if I compare, here you may get 7 is the optimal solution. But the greedy method you got 23. But in your when I apply the optimal solution on this 7, you are going to get it. How you may get it? How you may calculate this 7? That is the question. Now once you see here whether this 7 is giving path from V0 to V3 or not, once you check. V0 to V11, that means this way. V0 to V1, that is 3. Plus V11 to V22. V11 to V22. This one. This way. How much you have? 3. 3 plus 3. Plus V22 to V3. Only 1. That is 3 plus 3 is 6. 6 plus 1 is 7. Once you see that what difference is there. If I apply the greedy method, static method, by sitting here taking decision, you are going to get 23. You got 23. If I apply some logics on this, if I take a dynamic decisions on these calculations, I'm going to get 7. Once you see what difference is there with this greedy method and your method, how you got this 7? This you are going to get by using dynamic decisions, dynamic programming. Are you clear? This is the beauty of dynamic programming. Now, if you compare this with greedy method, what effectiveness is there? Once you see that you got 7, a good path, V0 to this and this to here and this to here. This is a path. This is the best path comparatively greedy method. By using greedy method, you got 23. Once you see what difference is there in that, we clear this point. This we got by taking additions according to stages. According to stages. This we call as decisions we call as sequence of decisions. If I'm going to apply the sequence of decisions on our calculation of the shortest path, we got 7. If I apply only one static method to calculate the shortest path from V0 to V3, we got 23. Very clear. That is the difference of static method and dynamic method. Static method is nothing but greedy method. Are you clear what exactly how the problem is constructing now? Are you clear what problem is there in this? Okay. Then one more problem also I'll show you here. Now also see here, this is S and this is G. This is the distance. Now if I apply the greedy method on this, what do I get? Greedy method, if I apply 1 from this, minimum is 1. From this, from 1, A to D is there, A to E is there. A to E 11, A to D is 4. That's why 4 you can take. Why? Because minimum. From D, 18 is there. Let's see 18. How much you may get? It is nothing but 20. This is by using greedy method. This is by using greedy method. Okay, are you clear my point? Then if I apply one dynamic logic or DP logic on this, what happens? Your value is 9. This is the shortest distance. How you got this? If I go like this, S to C is 5, C to E, F is 2, F to T is 2, and this is 9. If 9 distance, I can move from S to E. S to E. Are you clear? This is a effectiveness by taking a sequence of decisions on stages. Are you clear? By using simple dynamic greedy method, you got 23. Now, if I apply the dynamic decisions, I got 9. Are you clear? What is the merit of dynamic programming? I think now you clear with these 2-3 problems. Okay. Now I'll move to the next one. Now, multi-stage graph is also one problem in our applications, dynamic programming applications. So that you know as well, very clear. Comparatively greedy method, dynamic programming is inefficient, but you don't know how it works. How you are going to calculate by using dynamic programming the shortest distance between source to destination. That is a question. That method we are discussing now. What exactly multi-stage graph now? What is a multi-stage graph first? Multi-stage graph in the sense it is a directed graph and weighted graph. It is a directed graph and weighted graph. Then one more important point is we can partition into more than or equal to 2 partitions. More than or equal to 2 partitions that we call as multi-stage graph. Once again, listen. A graph consisting of P, E, vertices and edges. It should be a directed. First property is directed. Then second property is it's weighted. Then third property is we can partition this graph into 2 or more than 2 stages or partitions that we call as multi-stage graph. Okay? Once again, listen. A graph consisting of vertices and edges, and it is a directed graph, and it is weighted graph, and it is partitioned into more than or equal to 2 partitions that we call as multi-stage graph. This is multi-stage graph. Clear now? Then here Then we have one example. I will explain with the example that is very easy. Also see that this is multi-stage graph. I'll explain all theory here, and I'll move to the problems. Okay. Now theory, you can. I'm going to send this PPT to you. You see the theory in PPT. What I'm explaining, everything is there in the theory. Don't worry about that. Okay. Also see here. These are the different vertices. Number of vertices are nearly 12. Then edges are there. Then that means this graph is consisting of edges and vertices. Then it is a directed graph. All edges there we have a direction. It is moving to S2. It is moving from S2. This is directed graph. And third is it is a weighted graph. Each edge there is a number. This we call as weight. This we call as weighted graph. Then third property is what? It is partitioned more than or equal to two partitions. That means what? This is one partition. I can do it. This is one partition, and this is one partition. Partition. This is like this. This is one partition. This is one partition. This is one partition. Are you clear now? That means it is partition. The graph is partition. That's why this we call as multi-stage graph. Okay, clear? Now this starting point we call as source. This is symbol is S. S is nothing but source. And this we call as terminal or target or sink. We call as sink. This we call as sink, and this we call as source. Now, while you are moving here, thing is what? Thing is nothing but what is the problem here? Here problem is only that you have to calculate the distance between S and T, S to T. The distance in this is not distance, shortest distance. You have to calculate shortest distance between S and T. That is a problem. That's a multi-stage graph problem. Okay, this we call as multi-stage graph problem. The problem is what? S to T. But one more point you can write. You can calculate T to S also. If you calculate S to T, we call as forward approach. This we call as forward approach. And if you want to calculate T to S also, you can calculate. If you calculate like this, T to S, we call as backward approach. Very clear? Then we have two approaches. One is forward approach. You can calculate from S to T. Or you can calculate from T to S also. That is backward approach. Both the distance is same. Even this distance and this distance is same. Okay, are you clear my point? Now clear? Now, how you have to calculate the distances? Now, the thing is very important point is I already told you dynamic programming is nothing but a sequence of decisions. Each time you have to calculate the decisions. Each time, each stage you have to calculate the decisions, and you have to take a decision on the next stage by using this previous one. That is the logic here. Now, once you see here, logic is a simple logic, very simple logic. Now, here we have two terms I'm using here. This V is stages. This V1 is first stage, V2 is second stage, V3 is third, fourth, fifth stages. 5 stages are there. Now, I'm using two terms C. C of 1, 2, let us take. C of 1, 2, this one. C of 1, 2 is this C, only small c represents the cost of edge. Cost of edge. That edge, particularly 1 to 2. And if I write C of 9 to 12, let us take 9 to 12 is nothing but cost of edge. What is that? 4. Then 1 to 2, what is the cost? 9. That means this cost of edge I am representing with C, small c. Okay. Then one more point is cost. Cost also I am using. Cost of 1. Cost in the sense this one. Cost COST also I am using. COST in the sense I am using this cost as my one. That is nothing but the total distance, total cost, distance in terms of cost I'm using. I'm calculating Cost of this is nothing but, let us take, I'm using cost of first stage, first vertex. That means what? Cost of from this B5 stage to this stage. This distance we call as cost, COST. Are you clear? Cost of I comma j. This I am going to represent with one. I is vertex. J is represent the stage. How many stage? Sorry, I is stage, J is vertex. For example, it's a first stage. That's why cost of first stage. This cost of this vertex. What vertex number is 1. Cost of 1 comma 1. 2 terms I'm using. Small c I'm using. Cost COST I'm using. COST of 1 comma 1 is nothing but the distance between the distance between B1 to B5. That we call as cost. Okay, are you clear now? What is this? Now, how I'm going to calculate here? How I'm going to calculate this? Once again, listen. Once again, listen. S is starting vertex. This we call as source. P is ending vertex. This we call as target or sink. Okay. Now there is 3 conditions. One is this graph should be directed and it should be weighted and it should be partitioned at least 2 partitions or more than or equal to 2. At least 2 in the sense more than or equal to partitions. These partitions I am representing. Okay, very clear. Now, what is the problem here? This is multi-stage graph. What is the problem here? The problem is nothing but you have to calculate the shortest distance between source to target or source to sink. Okay. Now, how you are going to calculate? Here I am using 2 terms. One is small c. Small c represents the edge, the cost of edge, each edge cost. That means c of small c of 1 comma 3. That means nothing but 7. C of 1 comma 4 is nothing but 3. That means cost of that particular edge we are representing with small c. And COST, that means COST. This is nothing but cost of cost of that particular vertex, particular stage from, that is the COST. That is nothing but this one. Okay, very clear now. Now here, this I'm representing, this cost I'm representing. For example, cost of this I required. For example, COST of 2 I require. Let us say COST of 2 is what? It is in second stage, second vertex. 2 comma second stage, second vertex. I represents stages, J represents vertices. Okay. Now cost of I comma J is nothing but up to here, from here to here, the distance of this. Cost of this plus this one. And cost of V3, that is nothing but 3 comma 6 is nothing but this to this. This I'm going to represent in terms of I comma J. I comma J, what happens once you see that? That is easy for you to understand. Okay, 30 and 30 is there, no? Okay, anyway, tomorrow also we'll discuss this multi-stage graph. I'll work on example on this. We'll stop at this level. Thank you very much.